impact of wave mixing on CICE score, well, mostly CICE. So, first a quick outline. We start with some motivation, and then I'll go through a few basic things about vertical mixing schemes and the mixing scheme in NEMO that we use. Then we'll look at what the effect is on CICE of our new approach, and then see whether it actually improves anything in the model, which is always nice. Then a bit of discussion, some conclusions, and I have a few plans and ideas for future work. So, the motivation, sorry, actually all stems from the observation that the wave climate in the Arctic is changing. So, because of sea ice decline in summer, there's more open water now, so just fetch is increasing, which just increases wave height quite straightforwardly. So the mixing or wave height is increasing overall, but also extreme events are increasing. So the picture on the slide is from the storm in 2012, where there were 5-meter wave height in the Beaufort Sea, which is quite extreme for the Arctic. Now, because of the increasing waves, people expect that mixing because of waves will increase in the Arctic, and the Arctic is a low mixing environment, so any increase in mixing can be important. Now, there's a problem with ocean models that wave mixing is not, well, in sea ice covered regions is done quite cruelly and not realistic at all. So we want to change that and make it more realistic. So basics on mixing schemes. So I'm using the NEMO ocean model, but just in general, Reynolds average models need turbulent viscosities and turbulent diffusivities. So just thinking about diffusivity, what we need in the end is a length scale for mixing to take place, and also a velocity scale, how much will happen. So for the velocity, what is done in the ocean model is it calculates the turbulent kinetic energy of the flow. Equation with all kinds of terms. So one of them, which account for surface boundary condition, is the energy input that you get from breaking waves at the surface. And then for length scales as well, there's different approaches, can be more simple or more complicated, but in the end, you just have an equation that needs surface boundary conditions. What the models use is it's called the surface roughness length. We'll go further into that on the next slide. Just want to mention for NEMO, there's two mixing schemes that are used a lot, TKE and GLS. So we use GLS for this next one, and they have different biases in the way they treat surface mixing. So surface roughness length. Well, the options that are there, people are using, is first, simple one, use a constant roughness length. Something that is better already is to calculate the surface roughness length from the significant wave height. So there is some factor in between the two, like 1.3 or 1.6 sometimes. Anyway, so that brings us to leading knowledge by significant wave height. So either you parameterize it from wind, which is actually what all models do. You can improve parameterizations if you also account for wave age, rather than only the in situ wave wind speed. So that is what is standard in NEMO at the moment if you use GLS scheme. Now, the parameterization it uses is made for the North Atlantic, and actually it just ignores that there's any sea ice at all in ice-covered regions. So well, waves will be too high for sure. Other approach, what TKE does, it just switches off mixing with all of sea ice, which is not good either. So what we have done, we have significant wave heights modeled, which are modified by the ice cover, so the waves get attenuated when they go into the sea ice cover. One thing is that we are still ignoring the variations in the roughness of the sea ice itself at the bottom, because it will be in the pack ice more important actually than wave height. So what we do is we set a minimum roughness length that corresponds to the average that you should get if you account for various shapes that is used in foam drag. So the model. So the ocean model we use is NEMO, and I've used the sea ice model coupled to it. All the simulations here are 1 degree and just 10-year runs. The wave information we get is important. It comes from the ECWAM model, so from ECMWF guys. And we have what we call a wave in ice model or module that Lucia developed. And it affects waves into sea ice and attenuates according to flow size and sea ice thickness and so on. So things that we directly change in the model. So looking at the Arctic, first thing we change is just surface roughness. You see under the sea ice cover it's decreased now because waves are attenuated. Outside of sea ice cover there's some increase because we also account for part of the swell. It's not only wind waves. Then what happens is that our turbulent diffusivities are lower under the sea ice cover because we decrease the mixing. So let's go what actually the effect is on sea ice, which is the more interesting part. So this plot or slide shows the sea ice concentration and sea ice thickness. You see that actually the effect is quite distinct in distinct regions of the Arctic. So especially if you look at sea ice thickness, you can see that in the eastern Arctic, close to Siberia, there's a decrease in sea ice thickness now, while at the other side, overseas, there's quite an increase in sea ice thickness. So the change is between 5 and 10% of the thickness that was there already. Now, why does this happen? So, effectively, what we have done by decreasing the mixing, by decreasing the wave heights that are used in the model, is to decrease all the heat fluxes. And the reason why you can get opposite effects in different regions is that the heat fluxes in different parts of the Arctic go in a different way. So in the eastern part, you actually have warmer seawater close to the surface than below. So in that region, you are mixing heat down. Now in the Bofors region, the water at the surface is cold, but there is warmer water below. So there you are mixing heat up. So what happens now in the model that those temperature contrasts in both regions are increasing because you're exchanging less heat between the top and the bottom layers. Oh, wait, not too fast. If you take the vertical cross section, maybe it's more clear to see. So the red lines show the temperature profile in the Bofors Sea region, and the blue ones are for Eastern Arctic. So see for Eastern Arctic at the surface, there's actually quite a substantial increase in temperature, and temperature below doesn't change much. In the Bofors Sea region, it's the other way around. You get an increase in temperature at some depth below the surface because heat is getting stuck there in a way. It's not mixing up all the way to the surface. So what happens then is that there are changes in basal melt of the sea ice. So either decreasing in the Bofors Sea region and increasing in the Arctic region, Eastern Arctic region. So that will change our sea ice thicknesses. What also happens in the Eastern Arctic, we are decreasing sea ice overall, so exposing more open water, so we can have positive feedback there. We're absorbing more solar insolation, and it makes the effect even stronger of only just the mixing. Now, what actually happens overall? If you look at the integrated sea ice volumes, in the Arctic actually not that much happens, because they're opposite effects, they cancel each other out a bit. You do see there's some improvement in the mean sea ice volume. You can see a little bit of improvement in the seasonal cycle of sea ice volume, but also what you can see, actually the model is already almost completely matching observations, so actually it's already doing very good. Now, haven't showed anything about Antarctic yet, but actually in the Antarctic, the effects that you get through surface mixing are much higher than in the Arctic, and for the Antarctic, there is a substantial effect on the overall sea ice volumes because of the surface mixing. So what you can see from the plots, the one on the left shows our control run, and their sea ice volume in Antarctic is quite a bit too low, which is actually very common in the low resolution models. And our newest one on the right actually shows a significant improvement in the sea ice volume. So that's something I'm quite happy about. In summer it gets a little bit worse. We're overestimating a bit too much, but you know, it's not too bad. And then try to split out again this volume. We can look at ice concentration and ice thickness. So these are pictures for 1 year in September, which is the time of the year where the difference between the control run and our new run are greatest. So for sea ice concentration, some things are changing mainly along the ice edge, but it's not much really, doesn't really go in any particular direction. But for the sea ice thickness, there's quite a clear picture. See that there's overall increasing sea ice thickness, especially around the coast of Antarctica. That's where the impact is higher. So you've got more than 20 centimeters of extra ice there. So we're also not only increasing the overall volume of the sea ice, but also increasing gradients in sea ice thickness. So not going to go through the temperature profiles again, but if you do the same analysis, take the temperature difference between different layers, you can see that what happens is actually the same as in the Arctic. If temperature contrast is opposite in different regions around, closer and further from the shore. Now, something else you can look at is the mixed layer depth itself, since we're affecting mixing. So these two pictures compare the mixed layer depth in the model to observations from Cecilia. Well, she gathered all information. We put it in a very nice slide. So the line which is the error bars is are the mixed layer depth from observations, and the one with the dotted lines around are from the model. Now, these pictures are for two extreme situations in a way. So we look at mixed layer depth only on under the ice-covered part of the Canada Basin, and only at ice-free part of the Barents Sea. And so what you see that the standard model under the sea ice cover is actually over-predicting the maximum mixed layer depth in spring, and the new model is actually doing substantially better there. So now we are consistent with observations in spring. It's a bit worse at the end of the year, but the overall maximum mixed layer depth in the year is quite an important factor, because for because of nutrient fluxes, it dictates how much nutrients in the end you can reach. And for the parent sea, you see actually we don't really change anything at all. We don't deteriorate the mixed layer depth because of our new scheme. So that's good in a way. We can improve one thing without messing up something else. So some conclusions or summaries. We have seen that wave mixing has a substantial effect on sea ice cover. So if you look at sea ice thickness, so if you look at concentration or extent, it doesn't have much impact. We can expect that because of the increasing wave height in the Arctic, the wave mixing in the Arctic in the future will increase. What we've done effectively here is to decrease the wave height, so it's actually the opposite from what will happen in the future. And we had an overall increase in sea ice thickness. So what we might expect is that in the future we have extra decrease in sea ice thickness because of wave mixing. The effect is dependent on the area though, so it's not so easy to say what might happen, because one thing which will probably happen in the future is that areas where there is warmer water at the surface will expand. There's more less sea ice cover there. So in terms of model improvement, we definitely have a better sea ice volume in the Antarctica now. So this is my best simulation overall. And also we have an improved mixed layer depth on the sea ice in the Arctic. And this overestimating of mixed layer depth in the Arctic is actually quite common in models. So it's a good thing that we can improve that. So a few ideas of future work or plans. One thing that we might look at is that there's also mixing because of waves due to the shear between waves and the sea ice. So Fabrice has some ideas about that, so maybe you can look at that. One thing we definitely will do is to better account for the effect of the sea ice bottom roughness on mixing. So as I mentioned before, in the form drag scheme actually has all the information on topography, so we can use that to calculate the bottom roughness. What we have noticed with this simulation is that mixing schemes can actually have quite substantial impact on the sea ice cover you get. Well, this was just one process within mixing schemes, but using TKE rather than GLS, you can create different biases in different seasons in ice extent and ice area. So it could be nice to look at why it happens, because in principle mixing schemes should all do the same thing. I think that was most of my ideas and plans, so I can take your questions now.
Thank you, Stephanie. So, have a question? Is that Paul? Or
I was just wondering, could you say a bit more about where the waves come from in your model? It was a separate model. Was it a climatology or a daily output? Or?
So what we get from the ECWAM model is the wave information at some conservative distance from the sea ice edge, because the wave model and the sea ice model are not fully coupled yet. So what we do is we fill in the gap in a way, like we affect the waves close to the sea ice, and then when we reach the ice cover, well, you still let the wave just continue, but you also account for the attenuation of the waves.
Okay, it's time for one more quick question. Isla?
So following on this, the previous original NEMO before the modifications, they had waves somehow accounted for, and they had waves acting on the sea ice underneath the ice, and you remove that. Is that the way I understand it correctly, or there's something else to it?
Yes, we removed most of the significant wave height under the sea ice cover, yeah.
From the original previous NEMO version?
Yeah, from the standard GLS scheme that's in NEMO. Yeah,
Okay.
that's what it does.
Thank you.
Okay, so if we could thank all our speakers this morning, then we'll go to questions.